Welcome to the Problems Channel Season 2, Episode 32, the episode which I titled The LCM and the Difference, because in this episode we will use the eliminate and conquer problem solving approach in order to recover the values of two numbers if their least common multiple and their difference are given. Before we do that, however, as a traditional and friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much for your vote of confidence and welcome to our channel. And second of all, it is a good idea for you to go to the home page of this channel and in the channel's trailer section find the episode titled The Problems Channel How To. Watch that episode in its entirety, follow all the instructions that were given that episode, because in that episode we explain and motivate everything that we do on this channel. In the mathematical problem S2E32, we're asked to use the eliminate and conquer problem solving approach in order to recover the values of two whole positive numbers, n and m, if two units of information are given about these numbers. We're given the least common multiple, or the LCM, of these two numbers, which is 84, and we're given the difference between these two numbers. Let's say the difference between m and n is equal to 5. Yes, this problem can be solved in a number of different ways, and we will discuss one such way at the end of this episode. But the objective and the intended solution of this problem is to use a substantial and the meaty amount of the eliminate and conquer problem solving approach, and we explained how this problem solving approach works in the previous episode. If you missed it, it may be a good idea to find that episode and watch that episode in its entirety as well. As such, on the one hand, we remember an early number theoretic identity according to which the product between the least common multiple of two integers and the greatest common divisor of these two integers is equal to the product of these integers. And from that identity, we realize that if we can somehow say something meaningful and interesting about the greatest common divisor of two given numbers, then we can use that identity and solve two quadratic equations in, for example, the variable m. And we will discuss this approach at the end of this episode. But on the other hand, we want to parade a substantial amount of the eliminate and conquer problem solving approach. And here is one way in which that can be done. According to the definition, the least common multiple of two numbers is the smallest number that is divisible by both the number n and the number m. According to the fundamental theorem of arithmetic, each number at hand has its own prime factorization, or prime portrait, if you will. So that means that the number n is representable as a unique product of primes that make it up if the order of the primes in that product is ignored. Here I designate the primes associated with the number n with the lowercase p, p1, p2, and so on, and the number m. In order to distinguish the prime factors of m from the prime factors of n, I designated with pi, pi1, pi2, and so on, pi m. Each of these primes is raised to an appropriate power, and here is a positive statement that will be helpful for us. The fact that the least common multiple is the smallest number that is divisible by both numbers n and number m means that all the divisors of the number n and all the divisors of the number m must be present where? All such divisors must be present precisely in the number to which we refer as the least common multiple of the integers n and m. And these prime divisors or prime factors must be raised to the smallest power that honors the very definition that these powers must ensure that the resultant number is divisible by both the integer n and the integer m. In our case, what does that mean? Well, if we look at the number 84, which we're told is the least common multiple of two mystery whole positive numbers, n and m, then we can decompose that number over its primes, and its prime decomposition shown over here: 2 times 2 times 3 times 7. Now, if we unzip this prime factorization into all possible divisors of the number 84, then what shall we have? Let's do this together. Positive divisors of the number 84, according to its prime factorization shown on the lower right hand portion of your monitor, are the following. 1 is definitely it. Then what do we have? We have 2. We have 3. Let's try to keep this divisor sorted. What do we have next? We have 2 times 2 is 4. Then what do we have? 2 times 3 is 6. Then we have our number 7. We'll continue over here. 2 times 2 is 4. 4 times 3 is what? 12. 12. 2 times 7 will be 14. Will be 14. What else do we have? Then 3 times 7 is 21. 4 times 7 is 28. 28. Then 2 times 3 is 6. 6 times 7 is 42. 42. And then evidently 42 times 2 is 84. These are all the positive divisors of the least common multiple of our two mystery whole positive numbers. Let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Total number of divisors, positive divisors of the least common multiple of two mystery numbers whose values we are to recover, 84, is 12. And what does this observation mean that we made earlier about the presence of the divisors of the integers n and m in their least common multiple? That means that our mystery whole positive numbers n and m are hiding somewhere in that set of positive divisors of the number 84. And now our objective is to apply the eliminate and conquer problem solving approach to the process of the recovery of these two mystery numbers precisely by using the elimination rounds. The very nature of the problem at hand tells us that the specific order of the items in a pair, or the mystery whole positive numbers in a pair, is irrelevant. In other words, if we find these two numbers to be, let's say, 1 and 2, then the pair 1 and 2 is the same as the pair 2 and 1. And what does that mean? That means that for our elimination rounds, in order to follow or adhere to the first step of the eliminate and conquer problem solving approach, which is what? The first step of the eliminate and conquer problem solving approach is to identify all the possible variances of the local material. What is the local material this time? The local material this time are the divisors, the positive divisors of the number 84, which is the least common multiple of two mystery whole positive numbers. And what is the variance, or all the possible variances of the local material, mean in this case? Well, in this case, the possible variance, or all the possible variances of the local material, means all the pairs, or all the unordered pairs of items that can be picked from the set that we show over here, from the set of positive divisors of 84. And how many such unordered pairs can be formed or generated or chosen from the set of 12 elements? Well, according to one popular definition, this is basically the binomial coefficient 12 choose 2. And if we were to spell it out with specific numbers, that would be what? 12 factorial over 2 factorial times 12 minus 2, 10. 10 factorial, and let's carry out this computation through. the 10 factorial and the 12 factorial will cancel each other out and degenerate into what? 11 times 12. That's what remains from the 12 factorial once the 10 factorial is canceled out from it, over 2. And that means what? 11 times 6 is equal to 66. And that is our number. We identified, according to the first step of the eliminate and conquer problem solving approach, all our suspects. We rounded up all our suspects, so to speak. We now know the size of the suspect pool. 66 suspects are in our suspect pool to begin with. And in this specific, admittedly straightforward case, that number 66 can be obtained not just through a one popular definition of the binomial coefficient, but in the following way. Let's say we pick the first number in our set, that's number 1, and then what do? In order to generate all the possible pairs, of which number 1 already holds one spot, what do? Well, we pair up that number with how many? 11 remaining elements in the set. And how many such pairs will there be? Well, there will be precisely, write me down over here, 11 such pairs. And now, once we exhausted all the possibilities of forming a pair, of which one number is fixed, 1, we do what? We move on to the next number, number 2. But because specifically the order of the elements in our pair does not matter, normally, if the order did matter, we would have to form which pair with the second element? 2, 1. But that pair already was generated in this case, in the first scan through the set. So we can throw it out, and that means what? We pair up the number 2 with the remaining, what? How many? With the remaining 10 elements in our set. In other words, we pair up 2 with 3, 2 with 4, 2 with 6, 2 with 7, and so on. And there will be 10 such pairs. Now we throw out the numbers 1 and 2, move on to the next number, number 3. Here, again, normally if the order of the elements in a pair were significant, then we would have to form the pairs 3, 2, and 3 in 1. But we already accounted for these pairs through the first 2 rounds of pairings, and that means what? That means that we only pair the number 3 with whatever remains in the set, 3 and 4, 3 and 6, 3 and 7, and so on. How many such pairings we will have? 1, 2, 3, 4, 5, 6, 7, 8, 9. So now we'll have 9 such pairings. Now, once we exhaust all the possibilities with 3, we move on to 4. We do the same thing again because the order of the elements in our pairs does not matter. We do not pair up 4 with the previous elements. We only pair it up with the remaining ones. 4 and 6, 4 and 7, 4 and 12, and so on. How many such pairs we will have? 8. And once we're done with 4, we move on to 6. With 6, we will have 7 such pairs, and so on, all the way till we have only one pair left. With number 42, we'll pair it with 84. But what is this formation over here? Well, this is our favorite sum of consecutive whole positive numbers in first powers, and we know the formula. This is what? N times n plus 1 over 2. N is 11. So what do we have? 11 times 11 plus 1 over 2. And that number is precisely what? 11 times 12. 12 over 2 is 6. 6 times 11 is precisely 66. And now we begin our elimination rounds in earnest. For this segment of our episode, I took the liberty of erasing the material that we covered in the previous segments, but we all understand where did this material come from. What we have over here, I stretched this set of positive divisors of the number 84, which is apparently the least common multiple of 2 whole positive mystery numbers whose values we are to recover. And I also wrote down over here the initial size of our suspect pool of all the possible variances of the local material. 66 unordered pairs of suspects, which satisfy which as suspect may satisfy the problem statement. And here on the one hand, some of our viewers may say, Roman, look, the intellectual effort that we have to do to roll through all the 66 suspects is really not that big. In other words, there is almost zero intellectual voltage in the work that we have to do over here. How difficult is it to take an unordered pair of items, compute their LCM, and troll that value through 84? This is not that difficult, yes, but in some sense, this is perhaps some sort of monkey business or donkey work. Yes, it is simple on the one hand and straightforward on the other hand. It's tedious and perhaps even error prone. As such, we want to see if we can reduce the amount of that work. And here, the advice from George Poya from his immortal book, How to Solve It, comes in. As George Poya used to say in his immortal book, How to Solve It, have you used all the data? And the answer to that question is so far, no. In other words, so far we were able to extract actionable mathematics only from the first bit of information that we were given. In other words, we extracted some amount of actionable mathematics from the fact that the least common multiple of two mystery whole positive numbers is blah, 84. But we're also given the second unit of information, that the difference between numbers n and m, let's say I write it down over here, m minus n is equal to 5, is 5. And what is 5? Well, aside from being prime, which is a fact that we'll use at the end of this episode, that number parity-wise is what? Is odd. And that fact that the parity of that number is odd gives us an idea to conduct the following experiment. Let's say we construct a table where we investigate the behavior of even, E, and odd, O, numbers under the operation of addition. And what can we say over here? Even number and an even number is what? Is an even number. Even number and an odd number is odd. Even number and an odd number is odd, and the sum of two odd numbers is what? Even. And that, by the way, officially is a multiplication group of a multiplication table of a group that is isomorphic to a finite cyclic group, designated, for example, with C2, and that little group has many different incarnations. For example, under the operation of addition modulo 2, we have as the operation of the group, we also have which element? 0 and 1. And the group, the table over here will look which way? 0 plus 0 is 0. 0 plus 1 mod 2 is 1. 1 and 0 will be 1 mod 2. 1 plus 1 is 2. Mod 2 is precisely 0. What is the other one? Well, under the operation of multiplication, what kind of elements can we think of? 1 and negative 1, for example. Then in this case, 1 and negative 1. 1 times 1 is 1. 1 times negative 1 is negative 1. Negative 1 times 1 is negative 1. And negative 1 times negative 1 is 1. What's the other choice over here? Under the operation of XOR, our binary strings of length 1, which carry the values of 0 and 1, 0 and 1, form essentially the same table. XOR of 0 and 0 is 0, 0 and 1 is 1, 1 and 0 is 1, and 1 is 1 is again 0. What's another example from geometry? Let's say, well, all the rigid congruence motions of an isosceles triangle, of which there are only two, the identity and the reflection in its sole axis of symmetry. All these groups have different operations and elements in their nature, but structure-wise, they're all the same. In any case, what is the conclusion that we can draw over here that is useful for us? Well, from this observation, we know that when the sum or difference of two numbers is odd, then that means that the parity of these two numbers must be what? Must be opposite. Of course, we can show it formally that if one number is, for example, 2m, then plus minus 2k plus 1. Again, 2 can be factored out, n plus minus k, and then here we'll have plus minus 1, an odd number. So now we conclude that one number in the pair must be even, and the other number in the pair must be what? Must be odd. And how can we capitalize on that interesting and useful, tactically useful conclusion? Well, we can partition our set of positive divisors of the number 84 into two subsets. The subsets O for odd numbers, and what will be the contents of this subset? 1, then what we will have? 3, definitely 7, and by the looks of it 21. That's it. The cardinality and the size, because this set is finite, is known but to us right now. It's what? 1, 2, 3, 4. And the subset E, the subset of all the even numbers, will be what? 2, 4, 6, 12, 14, 28, 42, and 84. And the cardinality, and because the set is finite, the size of the set will be evidently 8. 8 and 4 is 12. This is our original set. And what kind of next step can we make? What would you do if you were solving the problem this way? Well, here you will bring in the so-called multiplication counting principle, because now what we're doing essentially, again, according to the second suggestion of the eliminate and conquer problem solving approach, we keep eliminating the suspects that are definitely not it. And in this case, we eliminate what? In this case, we eliminate all the pairs that consist of nothing but odd whole positive numbers, and we also eliminate all the pairs that consist of nothing but, even, and the pairs that consist of nothing but odd elements. And we only combine the elements or the numbers of opposing parity. And that means what? That the total number of such pairs will be given by what? By the product of the sizes. Technically, that will be the size of the subset O times the size of the subset E. It will be 4 times 8. It will be, let me write it down over here, 32. You understand what's going on over here, 32. So now you see, by using the information that was given to us in the problem statement, we managed to reduce the size of the suspect pool precisely by the elimination of the suspects that consist of nothing but even integers and nothing but odd integers. And thus we reduce by the size of the suspect pool by more than twice, from 66 suspects to 32. And I'll take a short break right now, erase the board and prepare it for the next segment. And in the next segment, we will further eliminate. We'll see how we can avoid dealing with 32 suspects. Very good. Now, instead of trying to chug along through 32 suspects, which we know how to construct, and computing the least common multiple of these suspects and controlling the result through the number 84, which we're given ahead of time, we can reduce the amount of work that we have to do even further by engaging in yet another round of eliminations. How can we do that? Well, let us go back to our subset of odd divisors of the number 84 and look at its size. 1, 2, 3, 4, 4 elements. So in some sense, all we have to do here is take each element in this subset of odd divisors of 84, carry out the computation plus minus 5, and compare the result of that computation with the subset of even divisors of 84. If the result of such a computation is in the subset of even numbers, we chalk it up to the suspect, and if it's not, we eliminate it. So now let's do this together. 1 plus minus 5, negative 4 is thrown out, 6, 1 plus 5 is 6, 6 is an even divisor of 84. So we write down this pair, 1 and 6, one suspect. We're done with 1. 3, there is no hope for 3. 3 minus 5, negative 2, we throw it out. 3 plus 5 is 8, 8 is not an even divisor of 84, 3 is gone. 7, 7 minus 5 is 2, 2 is an even divisor of 84, so we write down our next suspect, 2, and 7. 7 plus 5 is 12. 12 is an even divisor of 84, so we write down another suspect, 7 and 12. And with 21, we see there is no whole. 21 minus 5 is 16. 16 is not an even divisor of 84. 21 plus 5 is 26. 26 is not an even divisor of 84. 21 is eliminated, and voila, we're down to just 3 usual suspects. So now here, let me mark it down. After our third round of elimination, what do we have? We have only 3 suspects left. So now let's celebrate a little bit. Because we started with the initial pool that had the size of 66, then we reduced the size of the pool to 32, and now we reduced that size to 3. So now, since only 3 computations we have to do, we can safely engage in that computation. Numbers 1 and 6 are co-prime. Their least common multiple is 6. 6 is not equal to 84. What happens to this candidate, to this suspect? Eliminated. 2 and 7 are 2 primes. They are co-prime. Their least common multiple is what? 2 times 7 is 14. And 14 is not equal to 84. What happens to this suspect? Eliminated. Now we remember our another immortal character of Sherlock Holmes, due to the wonderful writer known as Arthur Conan Doyle. Whatever remains must be the truth, so we have to be careful over here. Again, precisely, one more time, I want to bring to your attention the fact that there is a fundamental flaw in the eliminate and conquer problem solving approach, because it has very weak powers of guarantee when it comes to doling out any sort of prediction of whether the culprit was included or was lassoed into the pool of suspects on the first step. So it may so happen that it will eliminate the only choice, and we will have carried out all this work for nothing. Business as usual in mathematics, business as usual in theoretical physics and computer science, happens all the time, and we need to be prepared for that. But in this case, 7 and 12, again, seem to be co-prime. The least common multiple of these two numbers is precisely what? Their product, and this time is 84, which is 84. So now here is our answer. The two mystery whole positive numbers are 7 and 12, and the difference between them is what? 12 minus 7 is 5. Again, we have to be somewhat careful over here, because under the operation of addition, whole positive numbers are closed, but under the operation of subtraction, the set of whole positive numbers is not closed. But in this case, we can cleverly swap the numbers in such a way that our difference is always a whole positive number 5. So now the answer to this problem is 7 and 12. There's only one pair of numbers that satisfies the problem statement in this case, and we obtain that answer precisely by applying the eliminate and conquer problem solving approach to the material given in this problem. And in the next segment, that will be optional, I'll cover the case where we will use precisely the early number theoretic identity, which says that the LCM of two numbers of two integers n and m times the greatest common divisor of these two integers is precisely the product n times m. You see, from this identity, we're given LCM. It's 84. 84. The greatest common divisor is up for grabs. Maybe we can say something meaningful about it, maybe not. But here in the n times m business, we can do what? N times, for example, n plus 5 to be thorough, and n, for example, n times n minus 5, and voila, we have a quadratic equation in n, two quadratic equations in n, if we can say something meaningful about the greatest common divisors of two usual suspects. This final segment of this episode is optional. If you're not interested in what we have to say about a different solution of this problem, then you can fast forward to the new challenge at the end of this episode. Meanwhile, for a different look at the same problem, we go back to an early number theoretic identity that is proven in most number books or textbooks on number theory at the beginning of the book, which says that if we have two integers designated n and m, then the product of their least common multiple and the greatest common divisor is equal precisely to the product of these two integers. In other words, the powers of the primes that make up the least common multiple and the greatest common divisor exactly factor into this representation of these two numbers. Now we know that the LCM of the two mystery whole positive numbers is what? 84. We're told as much at the beginning. Then over here we're told that the difference between two whole positive numbers is 5. So to be thorough, let's say in the first case the number, the integer, the whole positive number n is larger than its buddy. So in this case we will multiply n by what? By n minus 5. And in the second case we'll say that the number n is smaller than its buddy, in which case we will multiply n by what? N plus 5. And if we can say something meaningful about the greatest common divisor of these two numbers, then we're home free. Two equations that are quadratic in n, the numbers here is known, and we're home free. Well, here, in order to say something meaningful about the greatest common divisor of the usual suspects, we go back to the fact that we're told something about the difference. We remember that if a number d divides, this is a symbol for divides n, and it divides m, then we already covered this in the previous episodes. The number d as a shared divisor of these two numbers divides what? It divides the difference, it divides the sum of these two numbers, it divides an arbitrary k times n plus l times m, an arbitrary linear combination of these two numbers where k and l are integers, and that number will also evidently divide, obviously, the product of these two integers. But for us, what's interesting is the difference, because any divisor that is shared across two integers must also divide their difference. And since this observation applies to any divisor, it applies to the smallest, the mediumest in some sense, or to the greatest common divisor. And the bottom line of this observation is that the greatest common divisor of two mystery numbers must divide their difference, but the difference is what? 5, and 5 this time is prime, and 5 has how many positive divisors? Only 2, 1 and 5. That means that the greatest common divisor of the mystery numbers over here must be what? Either 1 or 5. Is that it? Well, not really. So now we go back and we again work with the definition of the least common multiple. In some sense, remember my previous observation that I wrote on the right-hand side of your screen. In some sense, the definition of the least common multiple is quite wide because it has to include all the divisors of both numbers. But here we're only interested in the shared divisors. In other words, if d is a number that divides both, then that number must be present in the least common multiple of these numbers, and evidently must be present how? In a way that it's a factor, a divisor of that number. And if this is true for any divisor, it is true for the greatest possible divisor. And what that means is that the greatest common divisor must divide the least common multiple. But in our case, we only have two choices for divisors, 5 and 1. 1 obviously is the smallest divisor for all integers. 1 always divides every integer, but what about 5? 5 does not integer divide 84. This is no good. If this number, if the least common multiple of two numbers was, for example, 85, then what? 17 times 5 is evidently 85. Yes, but now 84 and 5 do not work out nicely. In other words, 5, officially and pedantically, does not divide 84. So 5 as a factor is ruled out. The only, again, eliminated. So in some sense, we're using a little bit of the eliminate and conquer problem solving approach, admittedly over here in a very shy and meek way, so to speak. 5 is eliminated. The only choice for the greatest common divisor of these two numbers is 1. So now we know that these numbers pretty much have to be or must be co-prime, and this is what we saw exactly in the previous segment. 7 and 2 are co-prime. But now we write down two equations that are quadratic in n. So what will it be? N squared minus 5n minus 84 is 0, and then n squared plus 5n minus 84 is equal to 0. You see two equations that follow precisely from this early number theoretic identity, and that is already quite tractable. So here from this equation, what do we have? For the possibilities for the number n are what? So that will be 5 plus minus square root of what? 25 plus 4 times 84 and over 2. 84 times 4 is what? 336. 336 plus 25 is what? 361. We remember this from our middle school, or probably even before middle school, multiplication table. 19 squares is, let me write it down here, 19 squared is 361. And here is actually, I'll show you how it can be done in another way. But here we'll have what? 5 plus minus 19 over 2. And what are the possibilities? 5 is 19, 24 over 2, 12, or 5 minus 19 will be negative 14 over 2, negative 7. Negative 7 is eliminated. So 12 is one suspect. And in the other case, from this equation, what we will have? The only difference will be basically negative 5 over here. So here, the possible choices will be negative 5 plus minus 19 over 2. And here we will have what? Negative 24 over 2, negative 12. This is eliminated. Our numbers must be positive. Negative 5 plus 19 will be positive 14 over 2, 7. So here we have two choices, 7 and 12. So now how many suspects do we have? Well, we have the first suspect will be 7. In the first case, here the number n was greater. So here from 12 we need to subtract. From 12 we need to subtract 5 and obtain the suspect 7, 12. And in the first case, the number was smaller. So here the smaller number is 7. And to 7 we will have to add 5. Right? If this is 7, this is 7. 7 plus 5 is 12. So in other words, we have one and the same suspect either way. 7 times 12 is 84 precisely. So the answer is again 7 and 12. Precisely what we obtained in the previous segments. But evidently you can see that over here the amount, so to speak, of the opportunities to apply the eliminate and conquer problem solving approach was not that much, and that is why we suggested that ideally or an intended solution was the one that we showed in the previous segment. But if you solve this problem this way, that is fine too. We still recommend that you work your way through the material that we presented in the previous segments. And now this is it for the mathematical problem S2E32, and we will move on to a new challenge next. Before we jump to our next challenge, the mathematical problem S2E35, as I promised in the previous segment, here's a way to somehow realize, remember, or compute the fact that the square of 19 is 361. Here, for example, we can find an easy or a straightforward square from above, and such straightforward square is 400 because it is the square of 20. And then 361 can be represented as what? As the difference between 400, a straightforward square, 20 squared, and 39. Further, 39 is drilled down into what? Minus 40 plus 1. And 40 can be represented as 2 times 20. And from here, we represent it as a difference of two numbers, that is squared the square of the first number minus twice the product between the first number and the last one plus the square of the second number, and that is evidently 20 minus 1 squared, and that is how we obtain 19. Now in our next challenge, let's go back to our next challenge, which will be the mathematical problem S2M35. In that challenge again, we are asked to use the eliminate and conquer problem solving approach in order to show that no number in the form of 1, 1, 1, and so on, some number n number of ones where n is greater than 1, so n greater than 1 once, is never a perfect square. And again, to be sure, all this action is unfolding in base 10. In other words, we take numbers such as 11, 111, and so on, and we need to show that such numbers stand no chance to be a perfect square. And again, I'm using very straightforward, in some sense, toyish problems in order to demonstrate how the eliminate and conquer problem solving approach works. And for those who are interested in how that approach can really work, where it really shines and where it's really put on parade, I suggest that you look up the following, the so-called Freudenthal problem that was put together by this mathematician Hans Freudenthal. He lived between the years of 1905 and 1990, and this is also known as the sum and product problem. This is an absolutely wonderful, awesome problem that is basically nothing but non-stop eliminate and conquer problem solving approach. If I will have time and if there will be enough popular demand, maybe I'll put an episode that is dedicated precisely and only to that problem. If I don't, I suggest that you, on your own, out of band, so to speak, look up the problem, try to solve it, and see that one solution of this problem is basically a non-stop application of the eliminate and conquer problem solving approach. This is it for this episode. Thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will share my solution of the mathematical problem S2M35.